to see only the germinal and Western coupling between C6 CH2 protons, between C6 and C5, right? And between C5 and C4, and not between C6 and C4, right? But if I tell you that now record a TOCSY with 40, you would see some additional peaks start coming. And when you would record a TOCSY with 100 millisecond, then you would see everything is coupled with the other within the spin system. And this beautiful, amazingly powerful, robust technique is now available handy to every person for structural elucidation, because you may have 30, 40, 60, 70 different spin system in your molecule, and you would be able to record a separate NMR spectrum of each spin system theoretically. So it is an amazingly powerful technique. On top of it, TOCSY has also this capacity to tell you that with a different mixing time, you can distinguish between germinal, vicinal and long range coupling. So you can connect them together. You would know which peaks are appearing in COSY and which peaks are not appearing in COSY. Which peaks are not appearing in COSY are the long range couplings within the spin system. It's a very, very powerful technique, and that's why TOCSY is almost like a workhorse. This is a typical example in which you have a 2-sugar molecule, only different with the presence of an O methyl. This is the anomeric proton of this sugar, and this is the anomeric proton of the left sugar. Left to me, please. And you see that you have a separate spectrum of the entire spin system of this, and you have a separate spectrum of the entire spin system of this one. And if you ask them to give you the slices of 2D NMR spectrum, you would be amazed that you would get a beautifully nice separate NMR spectrum of each one of them. So these are the slices cut out of a 2D spectrum. They are not one-dimensional TOCSY, kindly remember. One-dimensional TOCSY is altogether a different animal, because you need to treat it in a very different way also. One-dimensional TOCSY depends on choosing a proton and then looking into the total correlation by spreading over time. In 2D NMR spectroscopy, you just selected a contour, the series of peaks like this. This is a series of peaks. And you just tell them to cut this piece for you, and you tell them to cut this piece for you, and then record it as a separate NMR spectrum. Amazingly powerful technique. And remember, you can do that with 3 different mixing times, 4 different mixing times, 20, 40, 60 and 100. And every time, if you keep these slices out of a 2D, you would see that the more and more peaks will start appearing. So this is not the proton NMR spectrum, but the spectrum of a coupled network. You would see only the COSY coupled, germinal vicinal coupled, and in 40 you would see some more coming up, and then in 100 you would see all of them are coming up as a whole spectrum. So the whole NMR spectrum appeared of a spin system when you have a longer mixing time. Okay? Yes, absolutely. That see, I don't want to go into lots of theoretical aspects. To be very honest, it is a multiple quantum coherence. Coherence transfer होती है इसमें. But for a simple understanding, kindly remember that all protons of this spin system are spin locked with each other by a train of 180 pulses. As a result, they all are almost on a same chemical shift, but their coupling is operational, and that coupling is appearing as a fine structure in your NMR spectrum. And please remember that TOXI is now available even with the simplest NMR machine, 200, 300, 500, 600, and it is a very, very powerful technique. And I showed you the example of our own work in which we had two different sugar molecules, and this is the whole spectrum of the molecule in which you see all of them overlap, the two sugar molecule. The sugar moieties have overlapping signals, both of them overlapping signals, but if you record TOXI 2D, and then you see a proton NMR of this particular and the other also. So you can record. Then the second thing which I started to discuss with you was H1 detected heteronuclear NMR spectroscopy. Sure. Mixing time is a time which is a constant. It is not varied. Always remember ये 20, 40, 50, 60 जो मैं आपसे कह रहा हूँ, they are constant for a set of experiment. इसलिए मैं कहता है I don't want to confuse you with evolution time. TOXI with 20 millisecond is altogether a separate set of experiment. TOXI with 40 millisecond is a separate set of experiment. 60 is a separate set of experiment. Mixing time is a time in which you see the consequences of T1 evolution and you give them appropriate pulses so they can mix them together and exchange the information. For instance, in this case, you see what you see. In this case, you see that during the mixing time, 180 Y pulses during the mixing time are actually used to lock the spins together, to bring them together by using an spin echo experiment. And in between the delta, split them, you again then put them together, they split them, again put them together. So every time you lock them together, they cannot change their position. Right, what position which they obtain at the end of a T1, kindly remember. When T1 was 0, they have never split it. When T1 is large, they have already split it. So spin echo would just keep them at right position. They keep them right at that particular position which has been determined by a T1 time also. So therefore, the protons of a spin system are locked with each other. You brought them to almost same energy level by giving a train of pulses. As a result, the chemical shift is almost close to each other, but coupling constant remain operational. Coupling constant, kindly always remember, no spin echo pulse can bring them together. Never. Please always remember that this is the key of understanding lots of NMR. By just understanding that the consequence of a 180 pulse in a homonuclear pulse sequence is spin echo, and consequence of 180 pulse in case of a coupling would never, they would always keep diverging from each other, they would keep going away from each other. Okay? So mixing time is a time in which you mix the spins together in a particular pulse sequence. There are pulses. Always remember you can have pulses and you can have just no pulses also. But what you do that at the end of the T1, you treat them by a particular pulse sequence or a time delay to magnify the effect what has actually happened during the T1. Okay, then we start discussing a very interesting experiment which is called heteronuclear H-detected NMR spectroscopy, and I told you that this is one of the most important development in NMR spectroscopy. We keep discussing that the most important driving force of development in NMR spectroscopy was initially the sensitivity. People develop large hardware, large computers, new pulse sequences, everything for increase the sensitivity. The whole concept of pulse Fourier transformation, NMR spectroscopy, polarization transfer, and even the inverse polarization transfer is for increasing the sensitivity of this very weak carbon-13. Very important nuclei on which most of the biochemicals and all the organic compounds are based on. Then there was a problem of interpretation. So you spread the signals on a second dimension. By using a two-dimensional, you can spread that to third dimension also by introducing another evolution time in the experiment. You can spread them into fourth dimension by introducing another evolution time into the system. And when you keep doing it, always remember that what has happened during the T1 time is the second frequency. What is actually happening during the evolution time eventually emerge as a second frequency, because that is your pseudo FID. And pseudo FID will give you a second frequency. Remember? Huh? So that's what we have learned. Then somebody said, why do we really need to? There was an understanding at that time also that when we do a normal polarization transfer, inept, basic fundamental experiment of polarization transfer, the first polarization transfer experiment which was designed, inept, in which you have a proton as a source and carbon as a recipient detected nuclei, which receive the polarization from proton. And then you have this very funny, interesting pulse, which antiphase of doublet of proton, which bring them on Z and negative Z. Always remember, this is the key of everything. And then you transfer the polarization from proton to the carbon. So source nuclei is proton, and detected nuclei is carbon. And as a result, you see an intensity enhancement, a sensitivity increase in it. Something very interesting appeared when people were doing inept, and when they were combining inept with the apt also. Number one, they learned that the carbon, which has no proton, would not appear. So it means that carbon is actually labeled by proton. So the information was actually reflecting into carbon, isn't it? No carbon, quaternary carbon primarily means that no proton. So when you see the absence of a signal, you say that there is no proton. Information which you got, you're not detecting proton. Kindly remember, you're detecting only the carbon. But even then you learned something extremely interesting about attached proton, and that was that the quaternary carbon has no proton. You also learned by using attached proton test that the carbon which has 3 protons move faster, and the carbon which has 1 proton moves slower, because they have a spin relaxation time which is less than the spin relaxation time of a metal. You also learned extremely important factor that because of the presence of proton, 2 sets of carbon appear in the negative phase and 1 or 2 sets appear as a positive phase. So what we have learned, an amazingly important observation was made at that time, that although you are detecting carbon, but information of proton is visible in it, isn't it? The proton absorbs some information about the proton, not everything. Some information about the proton is detected through carbon. People said, why can't we do it in a reverse way? Why can't we detect the carbon through proton? Right? In a normal polarization transfer experiment, you were detecting proton to some level. by carbon-13, you know. In the inverse NMR experiment, people said, why can't we detect carbon-13 or insensitive nuclei through proton, so-called H1 detected? Exactly inverse you need to do. You know, you do exactly inverse. What you do this time? You do, what is your source nuclei? Carbon-13. What is detected? Proton. You do exactly the same thing with the carbon as you have done in proton, inept, bilkul वैसे का वैसे, everything identical. You let the carbon split into two and then have an antiphase, and then you turn it like this, and then you see that the carbon polarization is transferred into proton. But you're not detecting carbon. What you are detecting right now is proton. And since you're detecting proton, it is a proton NMR spectroscopy. It's a proton NMR spectroscopy. By the same account, you labeled proton with the carbon, and you got the information of carbon on proton, encoded on proton. Remember, this coherence transfer and polarization transfer is a very simple understanding. Kindly remember that in inept you get information about proton which is not detected. In COSY 45, in COSY NMR spectroscopy, the same phenomena, and you have a modulation. When you have a modulation, you know which one is labeled with which one. So when you have a same energy level shared by it, the information transfer takes place. And that is the key of two-dimensional NMR spectroscopy. In this case, this is an inverse experiment. There's a whole set of experiments, lots of them, about 100 or over of them, and they are called inverse experiment, and they're called also H1 detected, proton detected experiment. Now, what is the purpose of doing it? Remember, carbon-13, whatever you do with it, you transfer a polarization of proton to the carbon, it remains insensitive. Remember, when I was discussing with you polarization transfer, I was always trying very hard not to remember the natural abundance, right? I keep telling you, don't remember the natural abundance, just remember the gyromagnetic ratio. I keep telling you. But this is a fact of life. You can't forget it. You know, whatever you do, carbon-13 remain a very insensitive nuclei, right? So carbon-13, whatever polarization transfer you do with it, may be good in some sense, but it remains a very, very, very insensitive technique. This is the reason that while you can carry out a good NMR experiment and 0.2 milligram of a sample, you cannot do it with carbon-13. You cannot do that. Carbon-13, you cannot record it by micromolar concentration. You always need to have some quantity of a sample because carbon-13 is inherently insensitive. Despite that, nobody is now doing anything else except polarization transfer. No experiment is recorded now. There is no laboratory in the world which dare to record a fully coupled C13 NMR. Or any laboratory in the world would record for a fully decoupled C13 NMR spectrum, only for the identification of quaternary carbon, only, nothing else. But actual NMR experiment, C13 NMR spectrums are always polarization transfer. Without polarization transfer, nothing is done. So this whole set of new NMR experiments were developed, which is called reverse or inverse NMR techniques. Very, very important conceptual development, not very different from the normal traditional polarization transfer. It is a polarization transfer in a reverse sense. Okay? And I told you yesterday that you need to have a different hardware for it. You remember I told you that polarization transfer, you need to have a proton-carbon probe. But if you want to have an inverse polarization transfer, you need to have an inverse probe also. What that primarily means? It means absolutely nothing, but the fact that in a normal polarization transfer, you need to have carbon coils which detect the signal of a carbon close to the sample, and proton coil in the probe away from the sample. So the closest circuit is the carbon-13. In case of an inverse probe, you have exactly ulta, exactly reverse. You have a proton coil, detection coil close to the NMR tube, and the carbon, which is your source nuclei, little away from the, so there is a architectural difference. There is a slight architectural difference. This doesn't really mean that you cannot record inverse NMR spectrum on a normal probe. You can do that, but sensitivity would not be that great also. And that is the reason why people always, now I would try to explain it to you what that primarily means by using, but let me first convince you that when you do a proton detected HMQC, heteronuclear multiple quantum coherent, there are two experiments, in fact there are three experiments, HMQC, HSQC, single quantum coherence, and heteronuclear multiple bond coherence. But in all of it, the phenomena is primarily same. This is inverse of an inept. Inverse of an inept, right? With the difference that in inverse of inept, your source nuclei is carbon and your detected nuclei is proton. In case of a normal polarization transfer, the source is proton and so remember, when you detect proton in inverse, although you decrease the sensitivity by dividing it with 1/4 of the gyro-magnetic ratio, but it remains very, very sensitive as compared to carbon-13. If you record a normal carbon-13 proton, buri se buri halat mein bhi, it would always be better than a carbon-13, right? Yani, kya kehte hain usse? Chalein chhode. This I like very, very much, and this is extremely easy. I hope you would like it. P means preparation, E means evolution, M means mixing, and D means deduction, finish at the end of the day. So this is a one experiment in which you transfer polarization from X to H and then H to X detect. There is no net increase in the intensity because you have done a reverse. This is the B, which is the most exciting one, the traditional polarization transfer. Here you have a source nuclei which is proton. You prepare your proton. Remember, you let it split. You let it split by coupling, and then you transfer the polarization to carbon, right? And you detect the carbon, right? So this is the carbon. X is carbon, nitrogen, or any other insensitive nuclei. The increase in intensity is about 4-fold. Remember? Polarization transfer, a normal traditional polarization transfer, the source is proton. When you give a 90x pulse, you let it split until they become antiphase. Then you give a 90y pulse which create a spin inversion, and then that's how you transfer the population of proton to carbon, and then you detect the carbon. And you have a 4-fold increase also. This is different. In this, this is a traditional inverse. When Muller first discovered this was again a contribution of H. Muller. He said that, can't we do it in a very reverse manner? Instead of this, shall we do it like this, that the source is a carbon. We do 90x, let it split into two components because it is a scalarly coupled carbon, and then when it becomes antiphase, give it, transfer the polarization to proton and detect the proton. Okay? Now you detect the proton and you detect the proton, but this X is already labeled on proton. X information is now transferred to the proton, and this is 8-fold increase. Now it is not the 8-fold increase in the carbon intensity, please kindly remember. This is 8-fold in comparison to a normal carbon spectrum. 8-fold in comparison to a normal carbon spectrum. But this is the most modern NMR, inverse NMR spectroscopy, in which the human ingenuity has actually solved, वो कहते हैं ना, two birds from one, क्या कहते हैं, one gun, one spoon, one, पता नहीं क्या, anyway, okay. Oh, you can kill birds with anything actually, depending where you have it. Okay. Now here you have an interesting experiment in which you have a source nuclei as proton. Proton is transferred by exactly the same thing as you have done. Inept. Kindly never forget inept. आप कुछ भी भूल जाए दुनिया में, but never forget inept. So you have this inept, and you have this particular antiphase, and then you do a spin inversion, transfer it to the carbon, and then you prepare this carbon to transfer back to proton. So what that means is that you give a 90 vipers, bring it back to the XY plane, let it be antiphase again, this carbon, and then you do a spin inversion. Same thing, reverse sense mein inept. Got. Alright. So once you have this, then you transfer it to the proton, and what you detect is proton. The source is proton and is proton also. Let me repeat it again. This is your 90x pulse. XY plane is split into two. During a particular time frame, it goes to the antiphase, right? Then you give a 90 vipers to bring it to the Z and negative Z, right? You transfer polarization to the carbon. And that is a position which carbon and proton both are on Z and negative Z. Now you give a 90 vipers to carbon, and that carbon comes on XY plane, right? You let it evolve until they become antiphase, right? And then you give a spin inversion pulse on carbon. And when you give a spin inversion pulse on carbon, you transfer it to the proton and you detect the proton. What you have done is amazingly powerful experiment in which you have used a positive polarization transfer to increase the sensitivity of carbon, and that enhanced carbon sensitivity was then back transferred to the proton. So this is my favorite slide. I like it very much. And this primarily means that you are actually detecting the proton. You're detecting the proton, and it is 32 times more sensitive as compared to carbon. Please remember carbon, right? Carbon. C. Okay, C, you have a traditional, the first inverse NMR experiment was a simple understanding that what you are doing with the proton, you can do it with the carbon also. As you were preparing for proton to carbon, you are now doing exactly identical with the carbon to proton. This is the traditional polarization transfer. Inverse polarization transfer. This is the inverse polarization transfer. It is possible as it is from proton to carbon हो सकता है, तो carbon to proton क्यों नहीं हो सकता? What is the benefit? Why? That is a question. This is a very, very valid question, and I don't know. No, but it's very simple. I think her question is very valid. That why you want to transfer the polarization of carbon to proton? You want to decrease the intensity of proton. But why? Because you want to label carbon. You want to see carbon in proton. You want to see carbon, you want to detect carbon through proton. Indirectly, this is an indirect detection of carbon. You're not detecting directly, you're detecting the carbon through its effect on proton. That is the reason. Now, there is a sensitivity decrease, as you said, is fine. But this sensitivity decrease is a proton NMR spectrum. And remember, proton is NMR spectrum even in very gai guzri halat. What is the English of this? Even in the worst case would always be sensitive than a carbon-13 NMR spectroscopy. Okay? Oh God, don't make my life so difficult, it's already very difficult. Okay. Oh, good. Oh my God. Can Maria, we do it alone? Can you come to my lab and then I can tell you? But, honestly, I want to understand, can you visualize what is happening? Can you visualize what is happening? For instance, what is happening in this is a purely inept experiment which you have seen, right? When you visualize this, is exactly the opposite. Here you are detecting a proton and you are doing exactly the same thing which you have done with the proton to the carbon, right? Doing exactly the same thing. Remember, carbon, you bring the carbon to 90 expulse, you bring this carbon is split into two parts, it goes antiphase, and then you give a 90 vipers, it goes to plus Z and negative Z, and it mixes with the proton, right? And then you mix it with the proton, because proton, remember, you didn't really brought proton to the XY plane yet. As you have not really brought the carbon to the XY plane in inept until it is reinforced and polarized, transferred. Then you bring it to the XY plane and then you detect it. You are doing exactly the same thing, that you start with the carbon, you do nothing with the proton, you are doing nothing with the proton, bring carbon to the XY plane, the carbon signal, it is a CH signal, is split into two parts because of a coupling, and then these two parts go to antiphase on X and minus, right? And then you give a 90 vipers to that goes to the Z and negative Z. H is not on this stage yet. H is still on Z. Remember, so you mix the population of carbon to the proton, and then you bring your proton to XY plane, and then you detect it, as you have done in case of this. Now, what is the use of having two polarization transfer? This is a beautiful question, and the answer is equally beautiful. Okay, the answer is beautiful because why you do polarization transfer in inept? Because you want to make your carbon sensitive, right? So when become carbon sensitive, when there is a fourfold increase in the intensity of a carbon polarization population difference, then it is more useful to give it back to the proton. Okay, so it means that you strengthen the carbon and then move it to the proton, not directly, but you first do an inept. That is the reason why I keep telling you that inept is an integral part of lots of NMR experiment now, even in inadequate also. Remember, inadequate में क्या करते हैं आप? Inadequate में what you do is the following. Carbon-13 satellites. Okay, carbon-13 satellite is 1 in 10,000. Right? If you can somehow increase the intensity of carbon-13 satellite by using a polarization transfer, isn't it good? Right? So you do inept, inadequate. You do inept, inadequate. Inept is an inherent process through which you increase the sensitivity. Inverse polarization transfer is a process in which you label proton with the information of carbon and you spread it on 2 dimensions. This is the most important. Now, you see, this is the most beautiful NMR experiment. HMQC heteronuclear multiple quantum coherence technique. This is a direct technique, very easy to interpret. On one hand, you have a proton chemical shift, and on the other side, you have a carbon chemical shift. You just make the line. This proton is connected to this carbon. This a straight vertical line, horizontal line, you get this proton is connected to this carbon. And remember, this carbon is separately recorded. This carbon is separately recorded and pasted on your NMR spectrum just for the ease of information. You don't need to have this, you can always say that this proton is connected to a carbon which is at this position. You don't need to see the carbon, but for the ease of interpretation, they record the C13 separately and placed it on the other frequency site. Similarly, this one which is at 5.68 is connected to a carbon, I don't know what. Idhar hoga iska chemical shift. I think something like 70, 80, 90, about 95, something like this. Okay. So it's very easy to interpret and it gives you a direct proton-carbon coupling. Now, question is, simple question. You see, what we have done so far before this particular NMR experiment was just bits and pieces. Either you connected carbon with carbon in inadequate, or you connected proton with proton in all different types of experiments like COSY or normal proton spectrum or whatever. What you have not done was proton-carbon coupling. None of the experiment was available in which you could see the proton-carbon coupling. This is the experiment in which you can see the carbon-proton coupling, heteronuclear coupling. And this is extremely sensitive because this is a proton-detected proton. What you have done 3 different things. Number 1, you use this tremendous sensitivity of proton to detect carbon, right? Tremendous sensitivity, which is after dividing with 4 remains several thousand-fold more than normal carbon, right? Tremendous sensitivity of proton to detect carbon. This is the number 1 thing which you have done. Number 2 thing, what you have done, that you have spread all these peaks on a carbon-13 scale. So you use the tremendous capacity of selectivity of carbon-13 to spread these proton peaks. Remember, these are proton peaks. Kindly remember, this is a proton NMR experiment. Please remember. Proton NMR experiment in which proton is modulated with carbon, and therefore it is coming in this graph, in 2-dimensional graph, close to the position of the carbon, which is its partner. So you see, you spread this, all of this overlapping is spread into tremendous large scale selectivity which you gain when you do a C13 NMR spectroscopy, 0 to 220. 2 things. Number 1, you use the sensitivity of proton to detect carbon. Number 2, you spread these protons on the scale of carbon, and therefore you avoid the overlapping. And number 3, which is again a very important property of HMQC, that if you have a geminal pair of protons, if you have two protons connected to the same carbon, you would be able to identify them, because both of them, assume Karlin, that you have this proton and this proton, both are on the same carbon, and both of them are on the same line of the carbon. So you would be able to distinguish between geminal partners, because two proton signals of a geminal pair would give the correlation with one carbon, a tremendous capacity of identifying. This gives you lots of problems, solution of lots of problems which you have faced when you were developing COSY, TOXY and other experiment. This is an experiment which provide you proton carbon. Thank you so much. This is capacity. This is a technique which gives you proton-carbon direct coupling with 3 advantages. Number 1, that you use the sensitivity of proton to detect carbon. Number 2, you spread all these proton signals. All of them are proton signal. किसी को कोई एतराज है इस पे? नहीं है ना? होना भी नहीं चाहिए. So you spread all of these proton signal on the scale of carbon-13, right? And number 3, you have the capacity of identifying geminal pair of protons, which you cannot do by any other technique in the world. Repeat it again. Okay. Technique, inverse NMR spectroscopy. One of the inverse NMR spectroscopic technique is HMQC, heteronuclear multiple quantum coherence, or HSQC, heteronuclear single quantum coherence. A slight difference in terminologies, end result is same. HSQC is generally used for proton nitrogen, and HMQC is used for proton carbon. Right? Philosophy same hai. Exactly identical philosophy. HSQC is used by biologists, biochemists, and HMQC is used by chemists, and HSQC is used by biologists because they were developed by biologists. Heteronuclear single quantum coherence, in which you see you do exactly the same thing, proton to carbon, proton to nitrogen, nitrogen to proton, inverse, inverse. HSQC, heteronuclear single quantum coherence. HMQC, you have a direct coupling between proton and carbon. It is an inverse technique in which you detect carbon through their effect on proton. So you're using tremendous sensitivity of protons to detect carbons, right? Indirectly. Indirectly का मतलब ये है कि these peaks which you see are all proton peaks, but they're spread because of the coupling partners. They're spread, right? Exactly the same phenomena as you've seen in correlated spectroscopy. COSY में आपने देखा था ना कि they were modulated because of the coupling partner. They are modulated also with the coupling partner, which is carbon-13, So you have tremendous capacity of detecting carbon by detecting the carbon indirectly through its effect on proton. The second advantage is that you spread these proton peaks, which are labeled by carbon, on the scale of carbon. when you, because ये सारे इसके साथ coupled हैं तो spread हो जाएंगे ना, they would all be spread, and when you spread that you will solve the problem of overlapping. You would be able to identify each proton with reference to coupling carbons, right? Number 3, that you would be able to identify geminal pair of protons, because when there are two protons which are coupled to the same carbon, it means it is a CH2, right? So you can, this is the only technique through which you can detect geminal pair. Remember, in COSY there is no distinction between geminal and vicinal, between W, between homoallylic, between allylic couplings of different type. All scalar couplings come so nicely in COSY like contour. But in this case you would be able to distinguish between two protons attached to the same carbon. Any question from any other university, please? Okay. And this is a very nice HMQC spectrum of menthol. This is the most downfill. This is the most downfill proton. So this is a proton. This is a proton which is now labeled with a carbon. So you make a straight line like this, and then you make a straight line like this. So you would know precisely that this proton is coupled to this carbon, and you do exactly the same thing. Here I will show you, let me try to find the coupling partner. For instance, in this metal, okay, these two contours are representing geminal proton. Okay, geminal, nahi, this is C3, geminal protons of metal. Can you see the contour? दो नजर आ रहे हैं ना? So these contours are the geminal pair which are correlated with the same. Let me try to find where is 4. 4 किधर है? 4 में ये देखें, 4, this 4 has two protons. One here, I'm sorry, this is 6. This is 6, yes. The C6 has two different magnetically different protons, and they are geminal pair, but both of them has a straight line with one carbon, right? What? This is really very simple, that both of these protons, which are the geminal pair CH2 of C6, have a same line with the carbon, therefore they are the geminal protons of the C6. So it's so easy. The C4 is here, C4, this one and this one, okay? And I think जो मैं आपको C3 बता रहा था, I'm sorry, it has a pair here. It has two pair, one here and the other here, and they both have a straight cutting line to one carbon. So you can identify the geminal pairs of carbons also. Advantage in enormous sensitivity. You can record HMQC in less than a milligram of a sample. If you want to record carbon-13, even with the polarization transfer, you need to have more than a milligram of a sample in a 300 megahertz. In this case, you would be able to have the chemical shift of all the carbons with reference to their effect on proton. This carbon-13 NMR spectrum is separately recorded and pasted on it. Please do not really think that it was generated through because it is not a carbon-13 NMR spectroscopy. It is a pure 100% proton NMR spectroscopy. Okay, now we move forward, and we go to let's say this is a neurominic acid or anyway. So you see that exactly the same analogy ये कौन सा होगा? C3 है. C3 is what? This one, right? So you see that these are two geminal pairs of proton of C3 which are correlated with one carbon, and you identify a proton and you identify a geminal pair. So you are capable of spreading this proton NMR spectrum with reference to the labeled carbon, and that's how you detect the carbon through their effect on proton. Through their effect on proton. Okay, interpretation is very easy. For instance, this O methyl is correlated with this carbon. There is another O methyl which is an ester O methyl is correlated with I don't know what is correlated with somewhere here or here. This is okay. Now, there is a variant of inverse NMR spectroscopy, HMQC. Yes.
HSQC and HMQC, these both techniques are for the heteronucleus. So I guess we can record both of the techniques for either carbon or nitrogen.
Yeah, actually you can record it both for proton and carbon. But HSQC was traditionally developed for proton nitrogen NMR spectroscopy. You can do it exactly identical procedure QC for proton carbon. There would be no difference in the spectrum. As I said, that they're essentially the same technique. There are slight difference in their Pearl sequence, very slight difference in their Pearl sequence. But they traditionally have been used by two different groups of people for two different types of heteronuclear interaction. Therefore, they are actually named differently. Now, HSQC and HMQC are almost similarly used, but kindly remember that HSQC has certain advantages over HMQC when you talk about nitrogen, because the nitrogen is a weaker magnet than carbon. Nitrogen is much weaker magnet than carbon, and therefore the sensitivity gain in HSQC is much more as compared to HMQC.
So what is the difference?
Well, sequence, there's such multiple quantum and single quantum we will learn when we'll go to NV spectroscopy. We will kindly remember that quantum is nothing but a flip of a particular nuclei. So there is a single quantum that primarily means that alpha become beta. When you talk about multiple quantum, that means alpha alpha become beta beta, right? So you use a different Pearl sequence and you get a different spectrum. One thing which I would like to tell you at this stage, that multiple quantum is not directly detectable. It's only single quantum which is detectable. So if you want to from your spectrum, like carbon-13, in this case, you do a multiple quantum coherence on it. Because multiple quantum conversion of alpha alpha to beta beta directly is not possible. There is no Pearl sequence, there is no energy level which can allow a proton to alpha alpha to become beta beta. This is always through alpha beta and then alpha beta beta. So multiple quantum is a technique through which you eliminate the possibility of looking into carbon, and this is a relaxation mechanism which we will discuss in the short while. Now, the variant of heteronuclear multiple bond correlation is again an inverse technique, exactly identical Pearl sequence. The only difference is that it has a filtered mechanism through which large one bond coupling between proton and carbon are eliminated. are eliminated, and you are only able to see the long-range proton-carbon connectivities. HMQC and HSQC is a direct coupling, 1-2 coupling. In HMBC, the 1-2 couplings are eliminated through a process. It's called quantum filtration. You eliminate large coupling between directly bounded proton-carbon, and what you see is primarily a coupling of a proton with a carbon which is 1-3, 1-2, or 1-4 bond away. In certain cases 1-5 also, but that is always in aromatic cases. Even 1-4 is only possible in aromatic cases also. But kindly remember this 1-2 is direct coupling, 1-3 is a long-range coupling, 1-4 is a long-range coupling. 1 means proton, 4 means at a fourth position there is a carbon or a nitrogen. So that's how you determine the now exactly identical philosophy. Inverse NMR spectroscopy, you're detecting the long-range coupling, long-rangely coupled carbon indirectly through their effect on proton. Number 2, that you have spread the long-rangely coupled proton in the scale of carbon. And number 4, you would be able to distinguish between long-range carbon connectivity even if you have an oxygen in between. So if I tell you that if you have a CH, then an oxygen, and then a carbon, then you would be able to see the effect of a proton with the oxygen, right? Because this is a 1-3 coupling. Now, this is extremely powerful, tremendously powerful technique, because whatever you have learned so far was largely bits and pieces. The TOXI will give you a spin system. Inadequate will give you coupling between carbon-carbon. HMQC will give you coupling between proton-carbon. It can't go beyond a spin system. It cannot really go beyond a spin system. HMBC is a technique through which you can look into the coupling between two different spin systems. And therefore, this is a technique through which you can cement. You can put these different fragments together. Amazingly powerful technique through which you can make structure fragment by using HMQC, COSY, TOXI, etc. And then you put them together with each other into an overall gross structure by using a long-range coupling between proton and carbon. Proton of one spin system and carbon of other spin system. This is the most beautiful technique. That's how you put different structural fragments together, one after the other pieces. Okay. So this is a very powerful technique. Generally the long-range couplings are in the range of tens. And remember, the direct couplings between proton-carbon are in the range of hundreds. Proton-carbon coupling is in the range of hundreds, direct proton-carbon coupling. The long-range proton-carbon couplings are in the range of tens, right? 7, 8, 9, 10, 12 is there. Therefore, you are capable of separating them away from each other by using a filtration mechanism. It is a very, very powerful technique, and there are lots of development. You can read through this. For instance, in this case, although this is not really two-spin system, but even if you have a two-spin system, for example, if you have a quaternary carbon here, you would be able to see the coupling between proton of H4 with C6. So you would be able to piece this fragment with this fragment together. You can link different. Assume that this is a CH nahi hai, right? You have a metal here, let's say. In that case, you would have two spin system. This is one spin system, this is another spin system, and there is the third spin system. You can link this methylene with C6 because the proton of this C4 will show coupling with the carbon and vice versa. And vice versa. You would also be able to see coupling between proton and C6 proton and C4. So that's how you link them together. The interpretation is extremely easy, but you see more peaks in HMBC because in HMQC you were only looking for a coupling partner. In this case, you are looking for its interaction with lots of other carbons. For instance, this is C2. So you make a straight line C2, right? This is H2 proton hai. Ye proton is coupled with C10, okay? I don't know where is C7. This is C7, 1, 2, 3 coupling. C5 is this one. Sorry, C5 here, C7 यहाँ पे. C7 नहीं होगा. This is C9, I'm sorry, this is C9. Okay, C9, and then you have C5, 2 is coupled with C5, 2 is coupled with C4, 1, 2, 3, and 2 is coupled with C8, right? This with this quaternary carbon, this carbonyl carbon. So you are capable of linking the fragments together by using an HMBC spectrum, You get a gross structure, you make bits and pieces. Always remember, when you record an NMR spectrum and do lots of toxi and noses and cosies and etc., you would get this peak. ये आपका fragment होगा. This is going to be your fragment, right? And this fragment, which has two methyl, a methine and a methine, which is a very downfield methine, you would see that all of them would be coupled with each other in toxi. Some of them will be coupled in cosi. And in HMQC, you would be able to see coupling between proton and carbon of different pieces. But what you would not be able to see the coupling between this particular fragment and the other fragment. And you need that, because you cannot assemble them together without having a capacity of identifying coupling in a long range. So this is a long range coupling between proton and carbon. C2, if it is coupled with C8, this primarily means that they are connected to each other through nitrogen. Okay? So that's how you determine the gross structure of a molecule. Okay, now what we have done, we've gone through a very extensive process of learning, and we learn a number of things. For instance, number one, we have learned that a simple proton NMR spectrum is recorded by a 90 X pulse and starting a detector. We learned that the intensity of signals can be increased as compared to noise by using a pulse Fourier transformation. We learned that a broadband carbon-13 NMR spectrum is a useful spectrum. It contains all the information, but it has a problem of multiplicity. You cannot interpret it. You have an interpretation problem. We learned that we can record a simple fully coupled C13 by giving a 90 X pulse to carbon and starting a detector, right? But we also learned that if you want to record a fully decoupled C13 spectrum, the only thing which you need to do is to frequency oscillator on the frequency of proton, and then you record a fully decoupled C13 NMR spectrum. We learned that also. We also learned that when you do that, you lost a very important piece of information, and that is the multiplicity. So we learned that there are techniques like attached proton test or Garrett spin echo, Fourier transformation, Gaspé, etc., through which you can determine the multiplicities. Then we learned that problem of sensitivity can be solved either by improving the hardware or by using an appropriate data processing, multiplying with certain factors. We also learned that there is a novel technique through which you can increase the intensity of a signal, which is polarization transfer. And then we learned that when we do polarization transfer, we see the other proton from which a polarization is transferred, detected through the nuclei, which is detected through. So it is indirect detection. Then we learned that this tremendous sensitivity increase will really make your carbon-13 NMR spectroscopy a practical provision, a practical process. Then we learned that attaching a polarization transfer experiment with EPT, you can also get information about the multiplicity. Then we learned that by using a total correlation spectroscopy, you can look into couplings of all protons within a spin system. Then we start learning about inverse NMR spectroscopy. Inverse NMR spectroscopy, we learn that we detect carbon through their effect on proton, and there is a tremendous sensitivity increase. And we learned that there is possible to put them together 1-2 coupling or 1-4 coupling or 1-3 coupling when we have HMQC and HMBC. What we have done so far is just putting bits and pieces together. We have done so far only the connectivity structure. We have not got a three-dimensional structure. We didn't even talk about conformation. We didn't talk about anything about the stereochemistry. What we have done, we just learned how to put proton, carbon, carbon, carbon together, link them together. This is a gross structure which has no conformation. This is a connectivity structure. This is not a real structure. The real structure required a three-dimensionality because except a few molecules, most of the organic molecule and almost all of the biochemicals are three-dimensional structure. They have a third dimension. They have a conformation, they have a configuration, and this is missing. What we have done until now is just technology, techniques, sequences, increase in sensitivity, putting bits and pieces together, looking into proton-proton coupling, looking into proton-proton coupling in the entire spin system, Wassenel couplings, germinal couplings, proton-carbon couplings, carbon-carbon couplings, proton-carbon long-range couplings, but we have done nothing to understand the dimensionality. And this is the last stage of structural elucidation. Without number one, starting from having a secure molecular formula to connectivity structure, gross connectivity structure, this is the one phase of structural elucidation. The most important phase at the end of the day is looking into the conformation and configuration of the molecule. Very important information, and that is so important that if you spend 20 years of your life and you develop a structure in which every carbon is rightly connected to every nitrogen, and every nitrogen is connected to every oxygen, and you have 100% correct connectivity structure, nobody would publish it. In chemistry, the structure has a dimensionality. It has a conformation and a geometrical conformation also. So you need to have that. If you do an X-ray, you get a gross structure with connectivity information as well as the geometry. If you do NMR spectroscopy, you first get the connectivity information and then you add the dimensionality into the structure also. This is only the second challenge. The third challenge is, if your molecule is big, what are the exchanges taking place in different groups? How in temporal dimension, with time it is changing its form and shape. So you go to a time scale also, different NMR spectroscopy, so-called exchange spectroscopy, XCs and other things. But is that we got the gross structure of connectivity, but we don't know anything about the dimensionality or the conformation or so-called geometrical consideration. And that is the most exciting, most important NMR spectroscopic technique called nuclear Overhauser effect. Albert Overhauser was a metallurgist, who did nothing, who had probably never seen an NMR spectroscopy. He just discovered the effect of interaction between different magnets in metal chemistry. Overhauser was not an NMR spectroscopist, but remember, जो NMR spectroscopist है ना, we are very nice, good people. We always respect people. We, even if they have done nothing, we still respect them. Okay, nuclear Overhauser effect, NOE. Kindly remember that O is always big O because it is a name. So you can't write small n, small o, small e, nothing. Small n, big O, small e, fine. Big N, big O, big E is fine also. अब आप कहेंगे what he is doing actually. But anyway, very important in structural elucidation. Well, I want to take you to a discussion which we had about 2 weeks ago. Remember I told you that when people have done a broadband decoupling, they discover extremely interesting phenomena. And that phenomena was that the peak intensity after decoupling was not the resultant cumulative collapse of a triplet into a singlet or a quartet into a singlet. It was more than that. It was more than that. And explain why when you decouple, when you start a radio frequency oscillator in the frequency range of a carbon, then why the intensity, proton, then why the intensity of carbon increased to threefold, NOE. This was NOE, which was later discovered that it is an effect of proton on carbon. A magnet which is irradiated is proton, and the magnet which is detected is carbon is doing something in between. There is something in between which is actually happening. But forget that. I don't want to go into sensitivity enhancement by NOE because that is not so more important, because you get 32% enhancement. You detect carbon into proton. It becomes things of the past when NOE was respected, because you get a slight gain in sensitivity of carbon. Now you have much fancier, much more sophisticated, much better techniques through which you can sensitivity of carbon or detect it through sensitive nuclei. What is more important in NOE today is its utility in the last stage of structural elucidation, in which you actually determine the effect of a proton on other proton which are not scalarly coupled, which are only closed in space, so-called dipolar coupling. Two different magnets close in space affecting each other is nuclear Overhauser effect. Based on direct through space interaction, so-called dipolar coupling. And remember, dipolar is just nothing but two magnets between nuclear spin. Related to nuclear spin relaxation, the phenomena of NOE Nuclear overall effect is a phenomena of understanding the relaxation. And here I would try to answer which people ask me about single quantum and a multiple quantum and a double quantum and zero quantum or whatever. All of that quantum typically employed during the last stages of structural elucidation provide information about the three-dimensional and molecular geometry. NOE, what Kurt Wittrich did, a Nobel laureate, he's actually used NOESY spectroscopy, which is a transient NOE, and he used NOE in the structural elucidation of protein, and that's what he got Nobel Prize. The contribution of Kurt Wittrich in biological NMR spectroscopy is largely based on his understanding that when you see interaction between protons and protons, you can use it to fold protein. You can use it to elucidate the confirmation of the structure of protein. He is the one who understands NOE more than anybody else in the world. And I'm afraid that if he died, nobody would understand that. Okay, depends on internuclear separation. It is not a scalar coupling. Remember, scalar coupling, TOCSY, even if you have a chain of 100 carbon, even if you have a chain of 100 carbon in a spin system, you would be able to see the interaction of all the proton within the spin system. It depends, scalar coupling, it depends the distance between two geometrically close protons. So for instance, you have this proton and this proton close to each other in space, and is actually translated into a nuclear arousal effect. Nuclear arousal effect. If I know that a part of my molecule, which is too far away, is showing an interaction with a part of the molecule which is at the C terminal, that primarily means that my molecule is actually folded. My molecule is actually folded in a very interesting way that I am able to see the interaction between two protons which are in distance far away from each other in terms of bonds, but which are close in space to each other. So it's tremendously powerful technique, which the real use of nuclear arousal effect, so-called NOESY spectroscopy, is in the structure of biomolecules like proteins. NOE was a domain of a small molecule chemist. We are the small molecule chemists. We do lots of small molecular structure, and we were using it. It was Professor Wittrich who used this NOE back in 80s, and he said that NOE can be used to determine the structures of the protein. Remember, what is the structure of protein? This structure is just a sequence. And sequence you can analyze by using a conventional sequencer, which is just hydrolysis of a peptide bond. You know which amino acid is linked to the amino acid. But actually the structure of the protein and its function is depend on its three-dimensional structure. The same protein has 4 different enzymes. Same protein, exactly identical protein, function in a different way, function as 4 different types of enzymatic reaction by just one single post-translational modification. Addition of a carbohydrate, addition of a phosphate group, or anything like this, it changes the whole conformation, and the functionality changes also. So the real structure of a protein is its 3-dimensional structure. And NOESY was used so profoundly and so strongly by Professor Wittrich group in Etihad, Switzerland, where they were able to demonstrate that they would be able to see the linkages in conformation by using an NOE. NOE is a dipolar, geometrically closed coupling which based on dipolar couplings. And it is, on the other hand, the interpretation of NOE is extremely tricky, very, very tricky. And that is the reason that in most of the book you would find a sentence. In E.G. Drome's book, when I was reading it long time ago, he said, absence of NOE doesn't mean that they are not close to each other. And not confusing. That if there are two protons which are close to each other, and if they are not showing NOE, this doesn't mean that they are not close to each other. The absence of NOE does not necessarily means that they are not close to each other. The presence of NOE means they are close to each other. Isn't that confusing? Interesting also, right? So, and one thing, NOE, one proton giving NOE on the other proton is not necessarily reciprocal from A to B to B to A. When you irradiate A and you see the NOE on B, it is not necessary that when you irradiate the B and you see the effect on A. God, I mean, it can be absolutely absent because it is all relaxation. It is the game of the multiple factor, which I really love very much, you know. Okay, so there are two different, excuse me, there is any, अभी तो मैंने पढ़ाना भी शुरू नहीं किया, हाँ, sorry. ये बिल्कुल आप सही कह रही हैं, इसका मतलब आप खत्म कर लें आज. Okay, you would know why it is still the technique of choice. And you would also know that despite all of its buraiya, is still very useful, right? Weaknesses. Buraiyon ka weaknesses hi hai na? Wrongdoings, sorry. Steady state, there are two different types of NOEs. One is called steady state or equilibrium NOE, and the other called transient or kinetic NOE. The steady state NOE is a one-dimensional conventional nuclear Overhauser effect difference spectroscopy, NOEDS, NOEDS. Nuclear Overhauser effect difference spectroscopy. It is a steady state equilibrium NOE. And there is another NOE which is called transient kinetic nuclear Overhauser effect spectroscopy, which is a two-dimensional NOE. Now you don't need to worry about the equilibrium. The only thing which you need to, nomenclature, the only thing which you need to understand the philosophy under the whole thing. Okay. But first let me tell you, for instance, this molecule. You see, in this molecule, the interesting molecule, this HA and HB are geometrically close in space to each other, right? And they are not coupled by a bond. They are not scalarly coupled. The only thing which is there, that they are actually close in space to each other. And it can be any molecule. It can be a very big molecule, several hundred carbons, and then folded away because of some reason, come close to HP. So it can be anything. So this is an NOE, and 45% of NOE, when you irradiate proton A, you see a 45% increase in the intensity of B. Intensity of B. So it's a 45% NOE. 45% NOE. That means that HA is close to HB. But if you radiate HB with HA, it's not that necessary that you would have a 45% increase on HA. No, not necessarily. It can be only 10%, 5%, 6%. I'll tell you the reasons, I'll tell you multiple of reasons why HA is different from HP. The HA has a lots of different partners, and it can transfer this energy to them too. While HB has only no partner which can accept the energy except HA. So the reciprocal NOE is very rare. I think if somebody can generate a reciprocal NOE, it primarily means that he has a symmetrical molecule. And if he has a symmetrical molecule, there would be no NOE anyway. So in this case, you see an NOE between a methyl and a proton, plus 18. Okay? This methyl, if irradiated, this proton is not that close to this proton, and therefore you see a very weak NOE, in fact, absence of NOE. This is an absence of NOE. Kindly remember that if I irradiate HA and if I don't get any NOE on HP, it doesn't really mean that HA is not close to HP. It doesn't mean that, because there are multiple reasons. But look into this. This is close to this. And you see a greater NOE, but it is far away from it, so you have very less NOE, even in the negative sense also. So now, if I tell you that this so-called steady state one-dimensional NOE, so-called equilibrium NOE, nuclear over-Rother effect, difference spectroscopy, this figures means absolutely nothing. Because when I say that there is no reciprocal NOE, it means that you cannot correlate this NOE with the internuclear distance. You know, ideally you would like to see that if there is 10% NOE, they are close to each other about 6 angstrom, and if it is 20% NOE, then they are about 3 angstrom, and if it, you would like to know the internuclear distances between proton by using NOE, right? Can't do it. Even today, it is a problem. You cannot do it. So unfortunate. Very, very unfortunate. People have been developing lots of confirmation model, try to fit it with the observed data, but it is practically impossible. Pulse sequence, very simple. This is the pulse sequence. So you have S and I proton. S and I proton, and S and I proton are not scalarly coupled. S and I proton are only close to each other in space, right? S is a source proton, source of NOE, right? I is interesting proton in which you have interest. Yes? I'm sorry, but यही है, लिखा हुआ ये पूरी दुनिया की किताबें, मुझे समझ में नहीं आता क्या है. I don't know what is the meaning. I think it came from a solid state NMR spectroscopy, inverted or something like this. But S and I, what you do, you carry out a selective pre-saturation, a soft broad pulse on S chemical shift. On the chemical shift of S, which is close to I in space, you give a soft, broad pulse for a long period of time. And when you do that, you are making I uncomfortable. Because I is receiving a 90x pulse also, and I would be detected. So I would have two different forces acting on it. One is this S, which is a constant pumping of energy into the system, and the other is 90x pulse, which you brought in order to see the X. So in order to see the I. So I has two different energies. One is a normal radio frequency pulse, and the other is a saturation on a proton which is close in space, which is not scalarly coupled but close enough in space to do something strange. Okay? And then you detect I. That is what the effect of S on I is. And this is the beautiful, very nice, easy to understand, although I can't claim that I understand this. I can try here. Okay, they are S and I, okay? S and I. S and I, both alpha, S and I both beta beta, S and I alpha and beta, and alpha and beta. Since they are close in space, they can share energy levels because they are influencing each other, right? They are influencing each other. Kindly remember that no NOE can be observed if it is 6 angstrom, more than 6 angstrom of a difference in the distance. Only those protons or any other nuclei which are closer than 6 angstrom can show NOE. More than 6 angstrom, you would never be able to see NOE because they do not share any energy levels together. So they are close enough in space, and you have now a very interesting situation. You see that this is the transition of S. This is S, okay, and this is A. Sorry, I. Okay, now I want to take you to bizarre world of relaxation. This S go through a transition. This W is a transition, and it's called single quantum transition. Only S has changed its orientation. Okay. In this, the I has changed its orientation, right? In this, the S has changed its orientation. And in this, I has changed its orientation, okay? The same, remember the inept, the polarization transfer diagram which I was showing to you, since they are influencing each other, this W1 is always a single quantum transition. Only one of the spin change the orientation. Okay? In a normal world, when you remember inept, in which I didn't really show you anything in between. Because there was a very, very interesting system in which you had just one pulses and you were transferring the polarization from one to the other. Here you have an amazingly high level of energy pumped to the system. Now, if you change this beta beta to alpha alpha, this is a double quantum transfer. This is a double quantum relaxation or excitation. This double arrow show you the excitation, and this is the excitation, and this is relaxation. This single quantum relaxation and a single quantum excitation. This is the single quantum excitation and relaxation. This is the single quantum excitation and relaxation. This is the single quantum excitation and relaxation. What is not allowed in the world of NMR spectroscopy is a double quantum excitation and relaxation. So it is not possible that you can pump both energy to create an alpha alpha going simultaneously without these steps into beta beta. It's not possible. And this particular type of transition or excitation or relaxation, if happen, we'll call a double quantum excitation and a double quantum relaxation. I said if happen, right? In this case, alpha beta is converted into a beta alpha. This is also a double quantum, right? But this is a zero quantum, right? Net energy is not different. But you need to change the orientation of both of them in order to achieve this one, right? So it is in real sense double quantum, but it is a zero quantum. Got zero quantum because net result is there is no net exchange in. So this is the diagram. I will tell you that this W1 is always operational. whenever you give a radio frequency pulse, the relaxation takes place by a mechanism which involves a single quantum relaxation. Always. Okay? Only allowed transition, allowed excitation, and allowed relaxation are single quantum relaxation. Okay. To achieve thermal equilibrium, only single quantum relaxation is allowed. Always also remember that this is the difference in population between different levels which determine the intensity of the signal. Always remember, always, invariably. But if you pump your system with lots of energy, then you see a play of forbidden relaxation. बिल्कुल ऐसा है जैसे कि if you want to hit a person so much that eventually he will hit your face too. Right? So this is pumping lots of energy into the system, that forbidden excitation, forbidden relaxation start playing its game also. This happens only in case of NOE. Only in case of NOE that you would be able to see a double quantum relaxation. A double quantum relaxation in order to achieve a thermal equilibrium. Kindly remember that system is very uncomfortable. I is very, very uncomfortable because I has a normal radio frequency pulse and a greater saturation of energy from the S, source nuclei. Now I want to take you a little further. I want to talk about the difference in population. Let's have N plus delta as a population of the lowest energy. Okay? This is N plus delta. And this is N minus delta, the highest energy. And these are the two N's of two intermediate energy levels. Very easy. The difference between S and I, this is a S transition. Remember, this is a S transition? Right? So the difference is only del, right? There is the difference in minus del. In this, the difference is del. So you see S and I appearing as singlets. Appearing as singlet. Kindly remember that they are not so close enough to cause any splitting of signal. They are not scalarly coupled. They are not scalarly coupled. They are not close enough to cause a splitting of signal. Kindly remember. Now, if I said that I want to saturate the system of S, I give a lots of energy to S. S is saturating the whole system. That primarily means that a part of the S is go from here to here, right? So it reduced. The population here is reduced, isn't it? ये आ रहा है ना समझ में? Full delta and half delta. And this was N, now this is plus half delta. Similarly, this was N, and now it is negative half delta, and it was minus delta, it is now negative half delta. So the population is transferred from here to here and here to here. ये समझ में आ रहा है नहीं? Very easy, that what you have done by saturating the S, which is close to I, you transfer a part of population from this to this and this to this. And it's very easy that there was a delta. You take half delta from here and put it here, right? And exactly here, this was negative N, and you take a half delta from here to here, which was a delta, it become minus half delta because half delta is with transfer. Now, if you look into it, the S would have no difference in population. There is no difference in population of S lines. So S becomes zero. There would be no peak in nuclear overhauser effect. When you irradiate S, you don't see any peak of S because S has died actually, gone. It has transferred its population to a different energy level. The I would of course be available, and this is a single quantum relaxation. So from here to here, कितना difference है? Delta का है ना? और here to here कितना difference है? Delta का. It was always a delta. I was always a delta. So you see no net increase in the intensity of I. No net increase in the intensity of I because only single quantum relaxation are functional. If I tell you that the system now is so uncomfortable that in order to achieve a thermal equilibrium, it allows a double quantum relaxation. Okay, this is a situation in which you would have a double quantum relaxation. It means a population from this is transferred to this, which primarily means that this population has decreased and this population has increased. As a result, you would have a greater than delta and a greater than delta also. The population between I is now greater than delta because the difference between this and between this and this has grown, because there is a direct transfer of population from beta to alpha. This is a forbidden relaxation. As a result of a greater increase in population, you see an enhancement of signal, and this is called positive nuclear over-Rauser effect. What has happened that by saturating S, pumping energy into S, you have forced a relaxation mechanism which is normally not allowed, which is not operational in case of single radio frequency pulses, right? It is only become operational when the energy of the system is unusually high. And when energy of the system is unusually high, that trigger a relaxation which is a forbidden W2 relaxation. Okay, but now this is another case. Because of some reason it is not happening. Okay, what is actually happening is a transfer of population from this level to this level, which is again a double quantum transfer, but it is a zero quantum transfer in terms of spin orientation. What will happen? The population difference between this and this would be less than delta, right? Because you have transferred a part of the population from here to here. Okay? When you transfer the population from here to here, the difference is less than delta. And similarly, the difference between this and this is less than delta also. ये समझ में आ रहा है? Okay, as a result, you see a negative NOE. Now I want to confuse you before leaving. ऐसे छोड़ दें. I promise that I would do it again, after we win, inshallah, semi-final. And if we don't, then you have to come and then pray and what. Inshallah, we will. Anyway, kal everybody would work. Because remember, everybody has to work. Because if we want to take this country up, we need to work, right? If we just watch cricket, anyway. Okay, चलो मैं भी देख लूँगा अगर आप ये excuse दे रही हैं. Anyway, let's see. Here you have a negative NOE. I want to confuse you to the limit. I want to tell you that there are lots of competing relaxations. There are lots of competing relaxation. There is a relaxation which is a W1 relaxation, single relaxation. competing with the W2 relaxation, competing with the W0 relaxation. And if all of them compete with each other, you may have no NOE. For instance, if W2 is not operational, if before W2 become triggered, because it's a triggering, remember energy transfer always takes place when you have a sync, when you have a radio frequency which come in resonance. Always remember. So if you don't have anything which comes in resonance to receive this energy for W2 relaxation, and W1 relaxation is extremely efficient, you see no NOE. Right? And if you have a system in which W2 and W0 both are operational equally, then you see no NOE also, because negative, positive become. So no NOE doesn't mean that they are not close to each other. Remember, so this is the game of relaxation. And this is the game of amazing relaxation. If I tell you that, don't ask any question. No, if I tell you that if in my system, if I have a slight impurity of insoluble material, or if I have a slight impurity, let's say an oxygen is there, then the oxygen would receive this extra energy and forbidden relaxation would never trigger. This forbidden relaxation would never initiate, because there was a sink through which energy could be transferred by using a T1 relaxation time, longitudinal relaxation time. Now that primarily means that you have two protons close to space, but there is no NOE. Because there was a paramagnetic oxygen and it received all the energy, as a result there was no net W2 operational. And when there is no net W2 operational or W0 operational, then you would not really be able to see any NOE. Okay? Number two, if this W2 is extremely efficient in a non-viscous solutions. W2 is a typical of a non-viscous solution because tumbling neighboring protons, tumbling neighboring solvent is capable of receiving energy for W2, right? Non-viscous, always positive NOE. But if you have a very viscous solution, in which tumbling rate is very, very slow, then you see a transition which requires no net energy change. There is no net change in energy. Remember, इससे इधर जाने में there is no net in energy. Therefore, in a very viscous solution, W0 is operational. So you get a negative NOE. But if you have somewhere in between, if your solution is viscous and non-viscous together, if you have somewhere in between a less viscous, not very viscous, what will happen? A nightmare, a problem. NOE is a nightmare. And I agree with Sarosh that why we are learning this, it is a nightmare. Okay, but it is a very interesting subject, and I think we'll go through this again because it is very, very important and it has lots of merit, inshallah, and we'll learn about the NOE, nuclear overall effect. We'll have, inshallah, next discussion after winning the semi-final, huh? Inshallah, on Thursday, right? Okay. On Thursday, similarly at 1:45, I hope it is all right for other people too?
Yes, sir, it's
Other
okay.
universities? Okay,
Yes,
thank
sir,
you so
yes.
much. Okay, ji, thank you. Allah Hafiz ji, Assalamu alaikum.
Excuse me, sir.
Yes?
So I was having some questions regarding inverse NMR
Sure, please,
because
go ahead.
actually I joined late and maybe I am asking the same thing which you have already explained, but sorry.
No, please go ahead.
So the first thing is that in inverse NMR we observed proton with C13. So what happened with proton with C12 relationship?
Yeah, that's a very interesting question. I'm sorry I didn't really respond to it because I didn't want you to confuse it. This proton with carbon-12 is overwhelming. 99% of the proton are with C12. And you eliminate these proton signal by a sequence called BIRD, B-I-R-D, BIRD sequence.
Sir, I read
This
it,
is
but I did not understand it.
Okay, this is a pulse sequence through which you eliminate the large polarization of proton which is coupled with carbon. And if you want this more in detail, I think you can read it in our book, Problem Solving in Solving Problem in NMR Spectroscopy.
Okay, sir, thank you very much.
But is actually explained in quite a detail. But remember, this was a very valid question, and I am glad that you actually asked that you have a proton C12 also. But this proton C12 is eliminated by a BIRD. When you remove the BIRD, then you always have a polarization transfer from proton to carbon. Remember, the modern inverse NMR spectroscopy doesn't really need a BIRD sequence. I want to tell you, because of a simple reason that from proton to carbon transfer and the carbon to proton transfer would only take place when you would have a C13 in between. So the modern HMQC spectrum, which is called modern inverse NMR spectroscopy, doesn't really require BIRD. That's why I didn't really go through that, because by having a two polarization transfer, you eliminate the possibility of C12. C12 doesn't really come in the picture because proton can transfer energy to C12, but C12 cannot transfer the energy to proton. That is only happen when you have a coupling spin half nuclei. Thank you very much. Thank you. Sure. If you synthesize a compound,
I have synthesized the compound and after NMR that the probability that is the natural abundance of C13 is very less as compared to C12. Then how we determine the exact structure of that compound?
you need to have a little bit more quantity of a sample, and then whatever the C13 is in natural abundance, 1%, by polarization transfer, you would be able to see C13 spectrum. Every carbon. Because probability of finding a C13 on every carbon is equal actually. You know, if you have a toluene, the probability of having methyl as a C13 and a carbon 1 as a C13 and the carbon 2 as a C13 is equal. Right? So you just need to have more of a sample. More of a sample in order to, and when you do a polarization transfer, you increase the sensitivity. Anything else? Thank you.